Acids and bases. So we're going to start with 3 different definitions for acids and bases. So Arrhenius defined an acid as being able to produce hydrogen ion in water. Bronsted Lowry simply defined an acid as an H+ donor, whereas the Lewis definition for an acid is an electron pair acceptor. So you want to remember that acids accept. The Arrhenius definition for a base is that it produces hydroxide ion in water. Bronsted Lowry defined a base as an H+ acceptor. And Lewis defines a base as an electron pair donor. So bases donate. So we have a problem. We have to label the acid and the base as Arrhenius, Bronsted Lowry, or Lewis. So if we have hydronium ion, it fits the definition for all 3 of the acids. Ammonia also fits the definition for all 3 of the acids. If we change the solvent to benzene, then now hydrochloric acid can only be defined as a Bronsted Lowry acid and a Lewis acid. Ammonia in benzene as the solvent can only be defined as a Bronsted Lowry base or a Lewis base. So you want to right now memorize that ammonia is a Lewis base. So that should be your go-to to remember a Lewis base, ammonia. So now we have a problem that is giving us some molecules, some ions that look different to us from what we normally would use as acids and bases, and we're asked to label them. So we have this oxygen, which is charged, that therefore makes it oxide, plus we have SO3. So what we're showing here is that this electron pair is attacking the sulfur, and this electron pair is moving over to make a double bond. So this electron pair is an electron pair donor that fits our definition for our Lewis base. So therefore, oxide ion would behave as a Lewis base. If this is the Lewis base, then the other molecule or ion, in this case a molecule, has to be the Lewis acid. So some terminology that we are going to have to be able to use is, besides labeling the acid and the base, so in this case we've labeled our base and we've labeled the hydrofluoric acid as our acid. It's in equilibrium. So our base is paired up with a conjugate acid. So this is our conjugate acid, and our acid is paired up with the conjugate base. So this is our conjugate base. So you want to really understand about the acid conjugate base and the base conjugate acid, not only for this class, but also for organic chemistry. So we have another example. In this case, we have cyanide ion. Here's our electron pair donor. It's attacking the iron +2. So the cyanide is a Lewis base, and the iron +2 is our Lewis acid. So we want to be able to show the electron movement here. So we start from the lone pair, and then the arrow points towards the receiver. So when you do your OChem, organic chemistry class, you will want to be able to do this. The next question is simply labeling the conjugates. So the hydrochloric acid is our acid. The hydronium ion is our, the chloride ion is our conjugate base. Let me get rid of that. So again, hydrochloric acid is our acid. Chloride ion is our conjugate base. In this case, we have water as our Lewis base, and we have hydronium ion as our conjugate acid. Okay, let's talk about acid strength. So for a strong acid, the equilibrium lies far to the right. You're going to want to memorize these strong acids. So starting with the HCl, you can use the periodic table because underneath chloride, underneath the chlorine atom is bromine and then iodine. So start with the HCl and then go use the periodic table so that you know that hydrochloric acid, hydrobromic acid, hydroiodic acid are all strong acids. So memorize those. Nitric acid is a strong acid. Perchloric acid is a strong acid. Sulfuric acid, the first proton. So memorize all of those. There are more strong acids than this, but this is a good starting place. So hydrochloric acid 100% ionizes to hydrogen ion and chloride ion. If we were to set up a Ka expression, it would look like this. But because the concentration of hydrochloric acid is so small, we get a huge Ka, 10 to the positive 7. The first hydrogen in sulfuric acid has a Ka of 10 to the positive 9. Then we also have a second Ka for the hydrogen sulfate. So this has a Ka2, and it's much smaller than the Ka1. This is, for the Ka2, is 1.2 times 10 to the minus 2. So if we look at a strong acid, so for example, we have perchloric acid as a strong acid. And so it becomes the sodium perchlorate. A strong acid has a weak conjugate base. A strong base has a weak conjugate acid. You are definitely going to want to understand this so that when you take OChem, it makes sense to you. Okay, we'll start with water next time.